In this lecture, we are going to continue our discussion of the LSTM and GRU. Previously, we discussed the GRU, and now we are going to move on to the LSTM. To recap, what did we learn about the GRU? First, we learned that the simple RNN unit by itself is problematic because it can't remember long-term dependencies. The way we solve this is, we make the hidden state the weighted sum of the previous hidden state and the new value for the hidden state, which is essentially the same calculation as the simple RNN unit. In this way, the GRU always has the opportunity to remember the previous hidden state, allowing it to carry that state forward in time, reducing the chance of forgetting it later. Importantly, we recognize that these gates, which decide whether we should remember or forget, are just binary classifiers. They are little logistic regression neurons, something we are very comfortable with. Now, we are going to move on to the LSTM, which is a little more complicated, but follows the same idea. Interestingly, when GRUs first came out, the initial research suggested that there was no clear winner between the two. It was reported that the GRU performed comparably with the LSTM. This made the GRU a great choice because it has less parameters and therefore is more performant than the LSTM. These days, the current belief is that this isn't true, and that the LSTM actually ended up being better. In fact, at the time I am making this course, this latest research only came out about a year ago, which is actually 2 years after I made my first RNN course. So that just goes to show how fast things move in this field. Experimental results are always changing our thinking about best practices and which techniques to choose over others. This also is a great example of my rule: machine learning is experimentation and not philosophy. I know for a lot of beginners, the approach they take is a philosophical approach. They would try to use logical reasoning to deduce which is better, the LSTM or the GRU. The LSTM has these merits, the GRU has these merits, and so on. Such things are useless. Please don't waste your time on philosophy. Instead, follow the example that these researchers have set and use experiments to decide which is best. There are 2 papers I've attached in extrareading.txt that you'll want to check out. The first is called On the Practical Computational Power of Finite Precision RNNs for Language Recognition, and the second is called Massive Exploration of Neural Machine Translation Architectures. They both conclude that the LSTM outperforms GRUs, and so, given the choice, I would probably choose the LSTM by default. So how does the LSTM work? Basically, you can think of it as like the GRU, but with more state vectors and more gates. Again, it's my preference to understand the LSTM through the equations, but if you find these visualizations helpful, then you can feel free to look at that as well. The first difference with the GRU and the LSTM is that the LSTM has 2 states. In addition to h of t, which we call the hidden state, we also have c of t, the cell state. Sometimes the cell state is considered an additional hidden state, so you actually might pass both of these on to the next dense layer. For us, we will usually ignore the cell state, so you can think of it more like an intermediate value that you calculate, just like the gate vectors. So you calculate it, but you don't actually use it to pass on to the next layer. So even though the LSTM has an extra state, you can still think of it as having almost the same API as a simple RNN and a GRU. It still outputs the final hidden state, h of big T. It's just that for the inputs, in addition to x of 1 all the way up to x of big T, and the initial hidden state h of 0, we also have the initial cell state c of 0. For the outputs, it's a little strange due to how PyTorch works. Basically, we'll get h of big T and c of big T, but the details might be surprising. But we'll discuss that more later in this lecture. Okay, so let's get to the LSTM calculations. I want to remind you that while this might seem complicated, it's not. Don't be scared by the sight of equations, but instead, try to see the forest for the trees. Each of these is just a neuron. once you start to realize that each thing here is a binary classifier or logistic regression, it becomes a lot simpler to interpret. So what do we see? First, we see that there are more of these gates. Specifically, we have f of t, the forget gate vector. Next, we have I of t, the input gate vector, also known as the update gate vector, analogously to the GRU. And next, we have O of t, the output gate vector. So hopefully this is easy to remember because the word forget starts with F, the word input starts with I, and the word output starts with O. Next, we have the cell state C of t. You might notice that this actually takes on the role of H of t from the GRU. Specifically, we have the weighted sum of two terms. The first term is just the previous cell state, C of t minus 1. How much of this we end up keeping is controlled by the forget gate, F of t, so it controls how much of C of t minus 1 we want to forget. The second term is the simple RNN term. How much of this we end up keeping is controlled by the input gate, I of t. And notice that this has exactly the same equation as the simple RNN, unlike the GRU. Now note that for the simple RNN term, we have the activation function f of c. This can be anything, but usually by default it's the tan h. Finally, we have the hidden state h of t, which is just a simple transformation on the cell state c of t. In particular, we apply another activation function f of h, which also can be anything, but by default it's also usually a tan h. We then multiply this by the output gate O of t. So the output gate controls which values of the cell state we actually pass through to the hidden state h of t. Note that in PyTorch, it's not possible to choose f of c and f of h individually, and in fact, you can't even change them from the default. As mentioned before, because RNNs are so complicated, they're usually programmed all in one module for the sake of efficiency, and they're not really composable like the other modules we've learned about. Of course, if you were writing your own LSTM, you could customize this any way you wanted, but its performance would most likely be suboptimal. So you can see that by building up our knowledge, first through simple RNNs, then GRUs, then LSTMs, we can make something complex like the LSTM seem very simple. It's nothing but 3 logistic regressions, or neurons, to give us the forget gate, the input gate, and the output gate. Then, the cell state is the weighted sum of the previous cell state and the simple RNN, weighted by the forget gate and the input gate. And remember, we want to offer the cell state the possibility to remember its old state so that we can learn long-term dependencies. Finally, the hidden state h of t is just a squashed version of the cell state with the output gate controlling which values are allowed to pass through. By the way, I say squashed because we use the tan h activation by default and it's not possible to change. So this is really not a hyperparameter you have to play around with. In terms of code, how do the GRU and LSTM work? As promised, these have the same or similar API as the simple RNN, so if all you wanted to do is plug in a GRU or LSTM in place of a simple RNN, it can be almost as simple as changing the name. Let's start with how to instantiate a GRU and LSTM. As you can see, it's almost exactly the same as a simple RNN. We pass in the number of input features D, the number of hidden features M, and the number of RNN layers to stack, L. I also pass in batch first equal to true, so that all my data is always n by something, instead of having the n dimension somewhere else. The crucial difference is that in a GRU and LSTM, there is no nonlinearity argument because it's not possible to change. Let's now talk about how the GRU and LSTM will be used in the forward function. First, let's discuss the initial hidden state and what to pass into the RNN. Conveniently, the GRU has the exact same interface as the simple RNN. As input, we pass in the data into the first argument and the initial state h0 into the second argument. As before, the initial state h0 is of shape L by n by m, number of layers by number of samples by number of features. For the LSTM, we also require an initial cell state. Luckily, because the cell state has the same dimensionality as the hidden state, we will also initialize this to L by N by M. Now, let's talk about how to interpret the outputs from the GRU and LSTM. As you recall, RNNs and PyTorch return two things, not just one. With the element RNN, we get 1H, which is of shape N by T by M, which tells us the hidden state at the final RNN layer for each sample, each time step, and each feature. The second H is of shape L by N by M, which tells us the hidden state at the final time step for each sample, each RNN layer, and each feature. In the GRU, it works exactly the same. In the LSTM, we have something similar, but not the same. The first thing that is returned is the same as what we get with the element unit, the hidden value at each sample, each time step, and each feature. The second thing is different. We get the hidden state H and the cell state C, but only at the final time step. So this second H will be of shape L by N by M, which tells us the hidden state at each sample, each layer, and each feature. We also get the cell state of the same shape, which means it's the cell state at each sample, each layer, and each feature. Unfortunately, I'm unaware of how you would get the cell states at different time steps.